Hello, welcome to Sustainability Modeling lecture number 10, entitled Flush It Down Your Toilet, Then Drink It. And from this title, you can surmise that actually recycling water is going to be a big part of the message. Now, the system dynamics model that I want to discuss in today's lecture, it's referred to as SEWA, a simple water model. And this is a collaboration among several individuals at several institutions. The point person for this work is Courtney Gustafson, who is one of my graduate students, and she's also a member of this class. She's taken this class. She wanted to learn a little bit more about sustainability issues and how system dynamics models apply to them. But I want to give a lot of credit to her work in this lecture. Now let me tell you what I have in mind for today's lecture. I think we'll give a little bit of an introduction to SEWA and to water management in general, and I'll talk very briefly about the SEWA project, and we'll go through the SEWA model formulation in Vensim and the model equations, and I'm also going to talk a little bit about this in my commentary for this lecture. We'll go through a few case studies for the continental United States, for Maricopa County in Arizona, in honor of the several number of students that we have from Arizona State University enrolled in this class. And we'll talk about also the case study that actually motivated the development of this model, which is the case in Somalia, which underwent a very severe drought couple of years ago, and there were some interesting results that we were able to pick up with this model. Finally, I'll do some concluding remarks and point out some future directions and expectations for this work. So I think a big issue with water management is that typically water is, when we talk about water, we're talking about it in the sense that it's a renewable resource, okay? And the truth of the matter is that even though it's considered an unlimited resource, it's really finite. So in many ways, it behaves as a limited resource. And the reason for this is because there's this dichotomy between hydrologic cycle processes in hydrology, hydrologic science, in which water moves through the hydrologic cycle in a perennial fashion. So water is always moving, and there's always rainfall being created, and water moving from one place to another. But on the other hand, water as a resource for human use, it's a vital resource. So water pretty much touches every aspect of human life, and yet water, even though it's sort of unlimited or renewable in the strictest of sense, there's an issue between the availability or the existence of water and the access to water by human populations. So I'm going to be emphasizing that in the lecture, and actually also that philosophy reflects itself in the SEWA model. Water has direct links to other issues of sustainability, that's food security, health, sanitation, and survival, as I just mentioned. And the purpose or one of the purposes of developing this model is really to help understand how the freshwater resource the supply of this freshwater resource, the access to this freshwater resource can be modeled. Okay. Here's a little cartoon that was, and there's the source of that, this figure, and it's basically used to illustrate that of all the water available on Earth, only less than 3% is fresh. It's a quality that can be used by humans for most of the activities. Of that 3%, most of it, nearly 70%, is tied up in frozen form. Glaciers, polar caps, ice. About 29% it's in groundwater, on water in the ground, and then roughly 1%, maybe less than 1%, is what's available in rivers and surface water bodies and lakes. So when you think about the big lakes, the Amazon, the Nile, I mean, in the big lakes. I mean, these comprise such a small fraction of the water available. These comprise, even when you put them all together, all around the world, less than 1% of a 3% of water available on Earth. So that's, I want to give you a little bit of an idea of the scale. And I think the other piece that we should mention again is that we're going to be going back to this issue of availability, because actually this pie here reflects essentially, and even this little sliver here, this less than 1%, this is really the availability of water. It says nothing about access to the resource that we need. Okay. Let's take a little bit of a step back and tell you a little bit about how the Seawall model has been conceived. Okay. What we have here is essentially a water, a generalized or simplified schematic of how water sort of circulates through this management cycle, and how it's tied to two major components. One of the major components, it's essentially what we call the Earth system, which is the remainder of the Earth, the atmosphere, the oceans, and how water, fresh water, okay, interacts with that piece. And the primary interaction, we'll see a little bit more, but the primary interaction comes through precipitation, okay, and I should say net precipitation, because there's an evaporation flux that goes out of the cycle back to the atmosphere. So that's one major piece, and we'll go back to this because this is part of the big picture of the Seawall model philosophy. The other component, of course, is one that we've been dealing with already in the class, and is population. And then population interacts with the water management cycle, essentially by generating demand for water for several activities. Anything that has to do from direct consumption to industry, irrigation, and energy generation, and all these issues. Okay. So what I want to focus today, and the Seawall model focuses on the water management, part of the equation. Okay. So that's where we're going to be focusing on. So let me move on, and let me tell you how this was implemented in Vensim. Okay. And so what I want to do here, I want to show you the general philosophy, and see how this was developed. Okay. The Seawall model has three primary stocks. It's got the population stock here on the upper left, okay, and that population stock is driven by births and deaths, like as many as we've seen. This model in particular has got an immigration rate associated with it, okay, and so that allows to consider when population is going into and out of the system. The other two stocks that come into play are water stocks, or water management stocks. One is freshwater sources. Now, freshwater sources are used to account for amounts of water that are available for use, amounts of fresh water that are available for use. So anything that has to do with lakes, rivers, groundwater, it's coupled, or it's captured in this stock. Okay. The next stock that comes into play is the freshwater supply, or the stored freshwater supply stock, and that essentially, it's the amount of water that is actually accessible because there's infrastructure, or there's means to extract it from the source to the process of withdrawal. Okay. Now, in there's a separate video to this lecture that covers the logic behind the Seawall model. In general, I just wanted to have a glance here of the logic of the model, not necessarily or at this point, not necessarily about all the relationships. We covered those in the Vensim model. Now, let's take a look at how this operates. I'm gonna focus on the water management piece, and then I'll tell a little bit more how humans interact with that water management piece. So essentially, the sources of fresh water are fed by a river inflow. So there is in your system, there is water coming in and river inflow is meant to capture all sorts of inflow, not only rivers but also groundwater as well at this point in this simplified model. So the river inflow and the rainfall, the precipitation rate that comes as sources. Okay, then those sources then are withdrawn through existing infrastructure and become, or a fraction of that becomes freshwater supply. Now, once water is in the supply box, a number of things can happen to it. The supply can be collected for consumption, so it can be piped to your house, to your industry, to irrigation fields, so there is a collection of water for consumption. Once water is consumed, a couple of things that can happen to it. Part of consumed water, it's treated as wastewater or as treated water, residual water, and the other fraction is not treated. It goes into runoff, a process called runoff, and runoff essentially either goes back to the ocean or it goes back to the sources. Okay, so and a perfect example of this is water. If water is used for irrigation or for irrigation of lawns or irrigation of fields, once it's used, it's not really treated anymore. It's basically goes away either to the oceans or it percolates into groundwater and actually may go back to the sources. The fraction of water that is treated, again, it can go into a treatment plant. Part of that water can be recycled, okay, and part of that water will not be recycled. The part of the water is not recycled, part of it will run off to the ocean again as a final receptor, or go back to the sources. Okay, again through infiltration into groundwater or through flow to a surface water body like a river or a lake. Okay, now no supply system is perfect, and even though we may want to use as much of the water for consumption as we can, the system may have leaks. So there's a leakage component here, and imagine that pipes, tanks, reservoirs, they all have leakage to some degree. So a fraction of the supply of fresh water that's available for use ends up as leakage. That leakage actually can do a couple things. Leakage can actually leak back to sources, or leakage can actually go into it can actually run off and go into the ocean. Okay, so that's a little bit of that picture there. Now, so by going back to the sources, you sort of close the loop because essentially the sources then get a little bit extra or get a little bit of feedback from the remainder of the system through these returns of flow to the sources. So every time some water infiltrates into the ground and becomes groundwater, it's going back to the source. Okay, whatever water doesn't go to the oceans will come back to the sources. Okay, let's see. So let's talk a little bit about the population component. And the population component essentially generates demand. Okay. This demand, it essentially once the demand side of the equation, as opposed to the supply side of the equation here, once that is established by population, then the distribution or the allocation of water becomes a little bit more clear, because the effective demand is going to drive how much water needs to be collected. Okay. As we will see in a few minutes, how much water needs to be collected is going to dictate how much water leaks, and how much water goes into every single of these components that go here. Part of the collection will leak, part of the collection will go into will be treated in sewers, and part of what's not treated in sewers will go back to the sources. So that's a little bit of the story here. So what I want to do now is go in addition to this logic, I want to go through the the specific relationships between variables that are in the Seawall model. So let's take a look at the sort of the not the logic, but now a little bit more of the formulation, the mathematical formulation in the Seawall model. As I mentioned, there was three stock variables: population X, freshwater sources Y, and freshwater supply Z. Okay. Let's look at the first variable, population. Population is controlled by a birth rate beta, a death rate alpha, and a rate of immigration that we'll call I. And what that translates to is an equation that looks like this, where we're assuming the dot notation for the rate of change of a variable. So x dot is the change of the population over time. Okay. Beta x is the rate of births, and alpha x is the rate of deaths. I is the rate of immigration. It's net immigration. So you can actually have immigration in, so population would increase. So if I is positive, this will cause x to grow. If I is negative, you have net migration out of the system, then this will cause x to decrease. So that's essentially the story. Not that different from what we've seen in most cases in which we've dealt with population. Let's look at the freshwater sources in CO1. This is the equation that has the most terms because the sources are going back and forth with positives and negatives. So the stock of freshwater sources is controlled by the river inflow rate phi right here. Okay, so river inflow is positive. The river outflow rate C, which is here, it's a negative. It's a it's a minus in the water balance. The precipitation rate P here, it adds to the sources. The evapotranspiration rate E, which subtracts from the sources. Then there's the rate of water withdrawal from sources into supply W. So this is the withdrawal of water from the sources into the supply of accessible water. Okay. Then there are additions, the return flows. There's the fraction of water that leaks that goes back into the sources, and this is lambda, that's here. There's the fraction of non-recycled water that goes back to the sources, and that's n. And then there's runoff, direct runoff to sources, which is omega. Okay, so this is runoff, this is a leakage return, and this is non-recycled return. Okay, so all these components add up to the change in the sources over time. Okay, let's look at the supply, which is the last of the three stocks, and the freshwater supply is controlled by the supply collection rate C. Okay. So once it's collected, it basically means that it's fed into the human system, and it subtracts from supply. The withdrawal rate W. So this is the rate at which water moves from the sources to the supply. So it adds to the rate of change of the supply. Then there's recycling. Okay. So recycling adds to the supply. And then there's leakage, which subtracts from supply. So those are kind of obvious and straightforward. So this is a little summary of the three stocks or state variables, their names, and their governing equations in Seawall. This table, by the way, it's found in this table, and a lot of the material that I'm about to show you is found in the Seawall draft paper that is in the readings folder for this lecture. So let's look at the key assumptions in Seawall that we have right now. One of the things that we introduced recently was a water rooftop collection rate gamma, and the general notion is that a fraction of the rainfall will fall on rooftops, and people will make use of that. They'll collect it and use it directly. So that's available directly for consumption. It doesn't have to be, withdrawn from the sources. So this is like a direct connection between rainfall and consumption. It's like you're basically taking water straight from the rain and using it. And this is certainly the case in many places that are water scarce, that use directly. We thought it would be important, particularly for developing countries and developing locations, to include this component. So that's there now. Essentially the river inflow, the outflow, precipitation, evaporation, the leakage rate, and the immigration are all exogenous variables. That means they're externally specified, and these are essentially links to other models that are out there, like climate models and demographic models, so other models like that. Withdrawal, consumption, recycling. Actually, gamma, it's not leakage. L is leakage. Gamma, it's rooftop collection. I mixed that up. So leakage, non-recycling, and the return flows. So this is the return flows lambda and omega. These are all functions of other models and parameters, so they're endogenously calculated. The model parameters are as follows. There is a demand per capita, and we're going to go through each of these in a minute, but I wanted to call them out. There's a demand per capita, and this is the amount of water that's demanded, or for which each individual creates a demand. There's a technology factor tau that is used to differentiate between more efficient and less efficient technologies to make use of water. There's a transfer efficiency, which is a measure of leakage in the system. So more efficiency means less leakage, and vice versa. And we'll talk a little bit about that. We introduce an assurance factor that is meant to capture. This is what I call a purely management factor, and this is used to capture how reliable we think the system is, and I'll explain how it's implemented in the Seawall model. There is a maximum withdrawal capacity, and so this is a maximum ability of the system to withdraw water from the sources. So there's a limitation on how much water can be extracted from the sources at any given time. There's a maximum recycling capacity. Again, it's a variable that's used to reflect the maximum ability of the water management system to recycle water. And there's also a maximum capacity of supply. So this is the maximum amount of water that the supply system can hold. If you think about all the reservoirs and the tanks and the pipes, this is the amount of water, the maximum that it can hold at any given time. Okay, so all of these are going to intertwine and interact with each other to generate some interesting dynamics. Then there's also three ratios, and these are essentially partitioning coefficients or partitioning fractions that indicate, for example, what part of the water that's consumed actually goes into the sewer. Okay, we already mentioned that part of the water that's consumed goes to the sewer. Part of it just goes directly to runoff. Okay, then there's a second ratio, the runoff to sources. So this is the fraction of water that goes into runoff that makes it back into the sources, because the rest goes into the ocean. And then there's the non-recycle to sources ratio. So this is the amount of water that's not recycled. So the fraction of water that's not recycled that goes back to the sources, because the other fraction will go to the oceans. Okay, so these are sort of partitioning ratios that are very useful to test some potential scenarios. And the last key assumption is that it's assumed that the leaked water returns to the sources with a time delay lambda. And the general notion here is that if you imagine, that there's a leakage in a pipe or in a tank or in a reservoir, and that water starts infiltrating or starts flowing towards a river, there is a time that it's going to take for that water to get back to the source. Okay, and that delay is essentially this time lambda, and we'll see how that again is implemented in the simulation model. So let's talk about water demand and try to see how all these equations come together. So the total demand of water, capital delta, it's little delta, which is the demand per capita. This is demand of water per person times the number of people, times the population. Okay. Now, because different locations around the world may have the same demand per capita, but have different capabilities of using water because they have better technologies or they have worse technologies depending on the situation. We introduced a technology factor tau, and by dividing the demand by the technology factor, we obtained something we're calling the effective demand. Okay. Now, the effective demand is a reflection not only of the demand per demand per capita or the total demand, but also the technology factor. So that's how it's calculated. The effective demand is the demand per capita times the population divided by this technology factor. Now, a technology factor equals 1, or tau equals 1, represents essentially sort of a baseline technology. If tau is greater than 1, so if then this indicates that you have a water saving technology, because basically for the same number of people and the same demand per capita, you would actually have a less effective demand if this number is greater than 1. On the other side, if tau is less than 1, if you essentially have a water, here's cold dispensing. It's essentially a water wasting type of technology. Then for the same number of people and same demand per capita, so the demand per capita can be interpreted as sort of a living standard. This is the amount of water that each person needs per day, and this is of course different in different locations. But under the same conditions, then a tau less than 1 will result in more demand or more water being used for the same amount of people and the same demand per capita. Okay, so that would lead to an inefficient water dispensing technology. So that's essentially the picture with demand. Let's look at water consumption and the transfer efficiency. Now, if you think about the amount of water that is actually consumed, so if you think about the fraction of the water that population consume as a fraction of the water that it's available or that is accessible for consumption, then you'll realize that because there's leakage, that there is going to be an efficiency of transfer between what actually gets consumed, which is C, and what would actually be available for consumption, which is C plus L. Okay, so C plus L will be like the total amount of water that could be consumed, but of that C plus L, only C gets consumed because L gets leaked. So this immediately defines a transfer efficiency eta. Okay, and only that fraction eta is what gets consumed. Okay. The nice thing about this simple formulation is that you can actually then link leakage to consumption by using the efficiency. So if you know the efficiency, or if you have an estimate of the efficiency of transfer, then you can immediately get an estimate of how much water is being leaked. Okay, and vice versa. If you know how much water is being leaked, you can get the efficiency. So it works both ways. Now let's talk about the supply components, and we saw that supply is driven by withdrawal, by consumption, by leakage, and by recycling. So let's take a look at those 4 components one by one. Now, and this is if you follow the logic, you'll understand what's going on here, and I'll try to explain this as carefully as possible. Let's look at the water withdrawal. Remember, this is the water that's withdrawn from the sources and converted into supply. Okay, and so what we're going to postulate here, the way we formulate this, is that the water withdrawn is going to be the minimum of one of 3 things. The minimum of these 3 things. The first one, it's the It's the source amount, Y, so this is the availability of water in the source, divided by the time interval. And by the way, this model runs on monthly time steps, so we're looking at monthly water balances. So this here, Y divided by delta T, it's essentially the amount of water in the sources on any given month. We multiply that by theta. Remember the assurance factor. And the general idea of doing that, the assurance factor is a factor that is less than 1, so it's a fraction. The general idea is that we use that as sort of a protection to say, well, you know, we don't know exactly how much water there is in the source at any given time, so we're going to assume that we even if we have a good estimate of it, we're going to only withdraw at a fraction of that. So that's why we multiply by this assurance factor. So that's one of the factors that goes into withdrawal. Then another way to look at the withdrawal rate is to look at from the supply side. Okay, and if you look at the supply side, if at any point in time or for any given month, you calculate the maximum capacity of supply minus what it's there already, this difference will give you the supply space available to take in more water from the sources. And so this here is, and again, divided by delta T, so you do it on a monthly basis, and again multiply by this assurance factor to be consistent with the comparison with the sources. Okay? And then of course you have the maximum withdrawal rate, which is the maximum capacity of the system. And if you imagine that you're extracting water from the sources, from pipes and from pumps and from wells, I mean this infrastructure has got a capacity, maximum capacity that cannot be exceeded. So you have to throw that into the picture. So if you compare any of these three, you take the least of them, and at any given month, that is the amount of water you can withdraw. Okay, so that's the logic behind withdrawal. Okay, let's look now at consumption. Okay, now consumption is going to be, this takes a little bit of thought to understand. So let me walk you through this. It's going to be the maximum of two values. Okay, now if you think about consumption is essentially it's driven, it's driven by demand. So you can, for example, at any point in time, if you have the water available, okay, you can just consume whatever you want. So that's basically this effective demand. So if you have plenty of water available, you can consume at will. However, if there is a limitation, okay, so if the supply available in a given month, so that's this ratio between Z of T and delta T, this is the amount of water in any given month that is available in the supply, multiplied by the efficiency, because we know there's going to be some leakage, and multiplied by the assurance factor, okay, again, to cover our backs in terms of the reliability or the uncertainty of these parameters. If this number is less in the demand, then you have to go with the lower, because this is the water you have available. So you take the least of these two, okay, and you subtract the rooftop collection. Why? Because rooftop collection is being used, so that covers some of the consumption need. So if you do that, and that number is is positive, then you consume that. However, if that number is negative, if you have if any of these numbers don't work out, then there is a scenario in which you can't consume any water. So this zero is here to make sure that if you run into a situation where you have no water in the system that you can't use, then you just have to, this is basically rationing. There's no water that's used that month. Okay, it's a little bit strict, but it's useful to have there just in case. So that's the logic behind the consumption of water. Okay, the leakage component of supply we've already seen, and it's linked to the consumption. So once the consumption is defined by the previous equation, then the leakage is just simply calculated with the efficiency. So that's a little bit more straightforward. And then there's the recycling. Okay, recycling follows a logic similar to the withdrawal. Okay, the amount of water on any given month that can be recycled is the least of these three components. Okay, let's see. The first one is, again, it's the amount of water that is that's available in the system. So if you look at the difference between the maximum supply and the actual supply, this tells you how much space you have for water on any given month, and you multiply that by the assurance factor. So that's one factor you compare to. Then there's this factor sigma. Okay, and sigma is defined here as the amount of water from the consumption and the rooftop. So this is the the total amount that's being consumed times sigma, and sigma converts this volume of water into the amount of water that actually goes into the sewer. Only that fraction of water that goes into the sewer can be recycled. So that goes here. And then the third component in that comparison is the maximum rate of recycling. Again, these pipes and this infrastructure that's able to recycle water, it's got a capacity. So whichever of these three is smaller, that's the amount on that given month that you can recycle. Okay, so that's the logic behind the recycling factors. Now let's look at water that returns to the sources, and we know that there's three amounts of water that return to sources. One is the runoff return, omega. Okay, and this is let's take a look at this logic. We know that C plus gamma is the total amount of water that was consumed. Okay. Sigma times C plus gamma is the amount of water that actually goes into the sewer, and 1 minus sigma times C plus gamma is the amount of water that's consumed that does not go into the sewer. Okay, and omega is the fraction of that is taken from, again, consumed water not in sewers. A fraction of that goes into the sources, and that's how the logic for omega is constructed. Then there is the leakage return to the sources, which we saw in the key assumptions, that leakage return to the sources is the leaked water delayed by a time factor lambda. So what this is saying is that whatever leaks gets to the sources lambda times later, or that lambda could be a month, it could be half a month, it could be 2 months, depending on the system. The non-recycled water that returns into the sources is found by multiplying. Remember this sigma? This sigma that we saw before, this was the amount of water that was consumed, okay, that was put into the sewer, okay. Now, if you subtract the recycling from sigma, then you get the non-recycled water. And if you multiply that by nu, which is the ratio, which is essentially the proportion of non-recycled water that makes it back into the sources, then you can calculate. That's the logic to calculate N. Okay, so that's how these return to sources are calculated. So here, this table summarizes essentially what we just saw. It actually has all the variables, the model variables here in the first column, and their denominations and how they're calculated. And you can see that as we said before, a number of them are externally specified, which means that you have to do some research to try to understand how much rainfall your site gets, or how much river inflow your site gets, and etc. And then the others are calculated using that logic, okay, that we just saw. So this is just a summary of that. And here is a summary of the parameters, okay, that appear with their names and their symbols. Okay, this is just a little bit of nomenclature of the Seawall model, because when you have a lot of parameters and a lot of these functions, it's good to keep track and summarize these. And all of these, again, are found in the Seawall paper that was distributed in the readings folder for this lecture. Let's take a look at some results, and as I mentioned before, we have 3 case studies: the contiguous United States, Maricopa County in Arizona, and Somalia. Let me walk you through some key results, and in the lecture folder you have the Seawall models for each of these cases, for the US, for Maricopa County, and for Somalia, that you can look at in detail. So if you implement this model in the contiguous United States, and it's really, the general idea here is that it's kind of difficult to capture the entire country with a single model like this, because this really doesn't differentiate areas that are water rich or more prone to having water, like say Louisiana and Florida, the east coast of the United States, or the Pacific Northwest, which are relatively water rich, and then you have these arid zones in the Southwest and in mid latitudes of the country where you cannot capture the same dynamics, because it's really not the same picture. Managing water in California is very different than managing water in Florida, and those two are very different than managing water in Texas or in the Northeast. So it's essentially an issue. But again, I'm showing results here for population, and given current demographic projections, and these are over the next 100 months, which is like 8 years or so, the population is going to continue to increase. But the more interesting comparison comes when you look at supply and sources, because this difference will tell you how well you're doing in terms of how much water you have in your sources versus how much water you need to have in supply to satisfy demand. So the blue curve here is the sources, and the red is the demand. And here, what's sort of indicated is the U.S. as a whole has enough water to go around for years to come. So that's a general message. But again, with that big caveat that this considers the country as a whole, it doesn't differentiate. And there are regions in the country that probably won't follow this pattern, which is the reason why we looked at the Arizona, Maricopa County, Arizona, where there was plenty of data to work with a model like this, and the results here show that indeed there was a situation. So this is the population curve, and population appears to be growing more or less quickly or more or less exponentially, and now we're looking at a much larger time scale. So we're looking at this would be here 100 years, so this is 150 years, and so on. So we're looking at a very long-term simulation. And if you look at the sources versus supply here, see you have a picture that's so inverted from when we did the model for the entire United States, where essentially your supply is already exceeding the availability of your sources, and because of population growth and increasing demand because of population growth, and maybe better technologies not being able to catch up, then you have a situation in which your sources are going to be drawn down, and then this is going to generate a decrease in the availability of the supply to keep up. And of course, when you reach a point where you run out of essentially run out of sources, then you start getting this very unstable oscillation where you really can't. First of all, you're going to be much below on your availability of supply to meet demand, but it's also the system's going to be very unstable. You're going to have these oscillations. Think about these oscillations in the same light that we looked at in the tragedy of the commons example, where we saw these oscillations where in a way that that's really the system was not able to be sustainable over time. Now let's go to the case in Somalia, which is the case that motivated this development of this model in the first place. Somalia had an interesting situation, is that in year 2011 there were in Somalia it's got a climate. It's kind of interesting because it has sort of within a year. It's got 2 rainy seasons. And what happened in 2011 in Somalia is that in both of these rainy seasons during 2011, the country received essentially 0 water, so it's completely dry, to the point where the United Nations declared a famine in Somalia, and we were actually able. This is part of the part of how we're developing this draft paper that we're working on, is to see how a model like this can be used to predict or project the set of conditions that would lead to famine in the future. Okay. So this is again the population plot, but let's look at at this one here. This is the sources versus the supply, and again you have a situation in which already from the onset the supply is exceeding the availability of the source, so you're running into an unstable situation. In this case, over time, the supply, the sources are able to recover quicker than the supply grows because of demand, and eventually they're able, the sources are able to sort of catch up with supply over time. However, we looked at this case in a little bit more depth than the others. We start looking at, well, what happens if, for example, if climate changes and you start getting, for instance, less rainfall, like it happened in 2011, and what happens is that when rainfall is equal to potential evapotranspiration, meaning that essentially you have sort of a net zero, water from climate, then your sources and your supply tend to run together over time. There's a little bit of a divergence after a number of years, but the divergence is not too big. But when you start getting lower rainfall, I believe in this model, the potential evapotranspiration is 15 cubic kilometers per month. That's about the value. So if you have less rainfall, then you can start seeing that that it has a pretty big effect, and immediately supply is going to outrun the sources. Over time, the sources sort of catch up, but there's a period of danger here if it starts even to run even slower rainfall. This difference extends a little bit more, although there's not a huge difference. You can see that it really displaces a little bit to the right, but not much. Then if it rains more, then this deficit sort of shifts to the left a little bit, and you're able to, the sources are able to catch up a little bit quicker. But you can see that this is a country or a water management system that is very vulnerable. One of the things that we also saw in Somalia is to look at the effect of other variables besides climate, and one of the factors that we looked at was this the influence of this technology factor. What happens if you can introduce better technology into a system? And we asked the question, well, what would be the time to deplete the sources of water under given conditions of use? And remember that the technology factor, oh, I'm missing an H here, oops, sorry. The technology factor, greater than 1 means better technology. Okay, so if you have better technology, what you see immediately here is that you're able to prolong this depletion time. This is, again, depletion time is the time that you run out of water sources. You're able to extend that, further out into the future. 100 years in this case for the supply, and for the sources, also, almost 100 years out into the future. Of course, if you use less efficient technologies, then situation, you get, your sources run out in half the time that it takes with better technology. So that was one question we asked, and then we looked at what happens if you can decrease leakage by increasing efficiency. So if you increase efficiency, again, the more you increase efficiency, the better off you are in terms of that depletion time. Okay, so that's sort of the idea with that. So these are kind of things that you can and the nice thing about doing it with models like this is that you can actually run these simulations over extended periods of time and sort of have generate some thinking into the future that you might not be able to do otherwise. Okay, and I'm going to point this out a little bit in my commentary for this lecture. So in terms of applications, of a model like this, water budgeting, projections, and doing scenario analysis like the ones that I just showed you, you can quantify the effects of improving infrastructure. Imagine that if you can reduce leaks or increase recycling or build more supply by building more reservoirs and better operational reservoirs. That's the kind of thing that you can do with a model like this, planning for that. You also quantify the effects of softer, policy interventions. Like, for example, what happens if you rationalize demand? What happens if you decrease demand by, having more efficient use of water? Introducing economic incentives. We haven't done this here yet, but certainly if we start looking at considerations in economics like we saw in the last lecture, like present value and future value and benefit cost analysis, certainly we're going to be able to identify scenarios that are better economically as well. So and analyze whatever scenarios we have now on the table from an economic standpoint. So that's something we're looking forward to doing. I already mentioned the looking at effects from changes in climate through rainfall and temperature, which affect evapotranspiration and the water balance. Other things that we have that are not here yet is linkages to human health effects, sanitation issues, impacts to ecosystems. So we would need to add linked modules to this, and so that's part of the exercise that continues with this. And this leads me to conclusions. So a model like Seawall can be used to analyze regions and locations. It needs to be refined and fine-tuned for that purpose, and can be used to support assessments and decision making, primarily with enough lead time to help avoid risks of either having too much water or deficient water supplies. So Seawall is really a tool for avoidance of mismanagement of water, and it's because it's really tailored to analyze both the hard side, the infrastructure side, but also the policy interventions. Lessons learned through these very preliminary exercises is that there's a need for reliable and accurate data, and I'll also talk a little bit about this in my commentary, but you can certainly complement your understanding of water management by doing modeling exercises like this, and understand better your uncertainty and your sensitivity of the results through these simulations. Now, it's always useful to remember that models are different than reality, and models should be viewed more to look at likely scenario outcomes and try to use that to support decision making. So the reliability of this model is going to depend on the reliability of the data that we have, and the reliability of the assumptions that we make, and only through a highly iterative process in which we try something, we run it, we look at the results, we see if it makes sense, if it gives us an additional insight. So these are more like thinking tools and tools to aid our understanding of these complex. You can see that even within this simple water management model, these systems are really complex, and this is just the tip of the iceberg. So I hope that you enjoy this, and that you can use this for for other purposes. Well, things that we're thinking about doing is to couple a model like Seawall or Seawall to a regional climate model to have a better handle on the climate components, particularly precipitation and evaporation, and as well as the river rainflow and outflows. These right now are being externally specified to Seawall, so we need to couple this into a climate model so we have a better handle on these. Right now we're sort of just saying, well, we're going to use this for rainfall, this for evaporation, but there's really no dynamic there. And also, as I mentioned before, the other frontier is the economic coupling. And I think this will be very useful to look at how these different variables are actually monetized, and to be able to run cost-benefit analysis and do do policy choice support based on economics and coupled economics. So that was pretty much it. I think I'm going to leave it at that. You can watch the Seawall model in this link, and I encourage you to do that because we go there into a little bit more detail of the model. And I also want to ask you to please remember to go over the readings for this lecture. I put in the readings folder in addition to Seawall, I put 2 system dynamics models. One that was done for Nevada, which is an arid zone, and that was done for South Florida, which is a wet zone or a wet area. And just so you can look at the contrast and the concerns and the issues and how those were approached. It's very interesting reading, and I encourage you to do it. So I think I'll leave it at that. So watch out for again the Seawall model video and Vensim, also the readings, and also my commentary that will be up shortly. I hope you enjoy the rest of the week. Take care now.